Hello again, physics friends. Today we're going to state Newton's laws, Newton's three laws of motion. It should be review. You should have seen this before, but I'm going to make sure we're all on the same page. And even if you have seen it before, maybe it's been a little while. And also maybe you haven't seen it presented in this way. So when we think about motion and mechanics, we have Newton's three laws that are going to play a central role. And we've already encountered one of them, Newton's first law, and I'm going to restate it here. There's many different ways to state Newton's first law. Here's another one. In an inertial frame, if a particle experiences no force, then that particle moves at a constant velocity. In other words, if an object is at rest, it remains at rest unless acted on by an outside force. Or if an object moving in a straight line at constant speed, it will continue to do so forever unless there's a net force on it. So that's Newton's first law, and in some ways, Newton's first law actually defines what it means to be in an inertial frame. Okay. Newton's second law is getting at how we change the motion of an object. Okay, this is saying, okay, we have this quantity called momentum, p, and the momentum of an object or a system will change in response to the net force exerted on it. And specifically, the rate of change of momentum in time is given by the net force exerted on that system. The other thing that I will point out is that Newton's second law is related to F equals ma. I haven't written it as F equals ma, but what we'll see is they are there are two ways of writing the same thing, although this way of writing it is true in general. It works at low speed, it works relativistically, whereas F equals ma is limited in its scope. So we'll see what the limitations are. Before we get there, I just want to identify the fact that you can write, you could call this Newton's second law in differential form. You can also express it in integral form by thinking about momentum and impulse and change of momentum and impulse. So if you integrated both sides of this equation with respect to time, then the left-hand side would become the momentum, final minus initial, and then the right-hand side becomes the time integral of f net dt. So we call this left-hand side here the change of momentum, and the right-hand side we call the impulse. So this is telling us that the impulse applied on a system is equal to the change in momentum of that system. Okay, and we'll come back to Newton's second law in a minute and talk about F equals ma and how it relates to this F equals dp dt expression. But first, we'll close out the trio and talk about Newton's third law. Newton's third law is maybe a little more subtle than it sounds, but its basic content is that objects interact via forces in a symmetric way, meaning that if one object exerts a force on another, there's a corresponding force. So let's see. If we have two objects, object 1 and object 2, and if object 1 exerts a force on object 2, then we have this arrow here, the force to the left on object 2 by object 1, I'll call that F21. That force, there's a corresponding force that is object 2 pulling on object 1, so object 1 is pulled to the right. These two forces have the same magnitude, okay, and they have opposite direction. So we can say that F12 is equal to minus F21, and there's two elements to that statement. The first is that the magnitude of the two forces is the same. And the other is that they point in opposite directions, so we can think about a unit vector, F12, put a comma in there. That unit vector might be called F12 hat. It's equal to minus F21 hat. So they have, these two forces have the same magnitude, and they have opposite direction. Okay. So where are we going here next? Let me just write this down, same magnitude, opposite direction. And where are we going next? Well, I'd like to say a few more words about Newton's second law and relating it to F equals ma, and then I'll say a few words about Newton's third law, pointing out some of the limitations of Newton's third law. So to start, let's kind of look at Newton's second law again, maybe a little more deeply now. in the following way. Okay, so Newton's second law tells us that the rate of change of momentum with time is brought about by a net force. In general, how do we write down the momentum? Well, if you want to account for momentum at any speed, we know that the momentum is equal to gamma mv, where gamma is that relativistic factor that depends on the speed of an object and the speed of light. And gamma is approximately 1 at low speeds. So for non-relativistic speeds, for that we mean speeds that are much smaller than the speed of light, gamma is very close to 1, so the momentum is equal to mv. And in this class, we are going to be working in the limit, where we are working at speeds much less than c, so our momentum is just going to be equal to m times v. But this expression, Newton's second law, written in this way, it does work even at relativistic speed. You just have to put in the correct momentum here. Instead of using mv, you need to use gamma mv. That's one point. So let's assume that we're working in this limit of non-relativistic speeds, and let's see what happens. Okay, so for non-relativistic speeds, we have the momentum is equal to mv, and so Newton's law, second law, becomes a time derivative of mv is equal to the net force. Okay, so if we then make one further assumption, if the mass is constant, okay, so like let's say you have a ball and it's being pushed around by a force and the mass of the ball doesn't change, then the force is only going to bring about a change in the velocity of that ball. So if the mass is constant, we can factor it out of the derivative. And now we see how we get to F equals ma, because the time derivative of velocity is the acceleration. So we are left with ma equals F net. So you may have seen Newton's second law written in this way, which is fine, but it assumes, one, that the velocity is much less than the speed of light, and it assumes, two, that the mass is constant. Okay, and we are definitely, in this class, we're going to focus on situations that satisfy number one, but we will definitely work in situations where the mass of an object is changing. And thinking about a rocket launching, a rocket going to space, that's a situation where the mass of the rocket is changing dramatically as fuel is burnt. Okay, so although we don't have to worry too much about this first assumption, we do have to worry about the second assumption. And so F net equals ma is not going to be, in general, useful for us. Instead, we are going to think about Newton's second law in this momentum form. One other thing I'll point out is if even in the case where we work in using this tool ma equals F net, and in this class we're going to start using a slightly different notation when we think about this. So we know that the acceleration is equal to the time derivative of the velocity, which in turn is the time derivative of the position. So the acceleration is the second derivative with respect to time of a position vector. So we're going to use a notation that is often called the dot notation, because we're going to be solving differential equations a lot with a lot of time derivatives in it. So instead of writing d squared r dt squared every time, you'll see us write r double dot or v dot. Okay, so the dot on top, it tells us that's a time derivative, and two dots means two time derivatives. Okay, so one of the challenges we're going to be faced with is if we have a so-called equation of motion that looks like this. We'll call this an equation of motion, in which we know what we have an expression that relates the net forces at play and the second derivative of a position. Our goal will be to solve for the position as a function of time by solving this differential equation. So whether we talk about Newton's second law as F equals ma or F equals dp dt, both of those equations are differential equations. And so classical mechanics involves often solving differential equations. And that's a skill that you practice in other classes and certainly will come to bear on the content of this course as well. So the last thing I want to talk about before we wrap up is Newton's third law. So let's first look at Newton's third law relativistically, and we can see why there's a problem right away. Okay, so here's the claim of Newton's third law. It's that the force on 1 by 2 is equal to minus the force by 2 on 1, and that's true instantaneously. So if the force somehow changes, both objects feel that different force instantaneously in that new instant. Well, okay, what do we know in relativity? Well, there's no absolute time, and events that are simultaneous in one frame are not simultaneous in another frame. So if you, quote unquote, turn on this force, then we're requiring this other force to also turn on at the same time, but same time is a frame-dependent statement. So there's no way in which those two forces can be equivalent to each other in all reference frames. So the fact that we know there's no absolute time, and according to special relativity, tells us that Newton's third law can't in general be true. So although it works well at non-relativistic speed, it in general is not a law of nature, shall we say. But in this class, we're going to focus on motion at low speed, the kind of classical limit outside of relativity, v much less than the speed of light. And so this statement will be quite approximately true, close enough that we can take it as true. Now, there are other examples of situations where Newton's third law doesn't hold, and the textbook goes into this in some detail, and if you're interested, I encourage you to take a look there. The specific example has to do with the magnetic force between two moving charges. So for that, you can check out the textbook. All right, but for now, I think we're going to wrap there. And until next time, take care and be well.